Okay, so last class we were looking at some constraints that are associated with the first law. And that's what I want to finish up and then look at the Joule-free expansion experiment, which is a kind of interesting experiment. So we know that the first law, you can write in differential form is just this. Okay, and since we know that dq is a heat capacity, which is path dependent, so we write that as C path, and there is a temperature dependence on that, so we can write it this way. And we know that dW in its most general form is P external times dV. And so this lends itself to suggesting that U is a function of temperature and volume if we hold N constant. And so for any changes in differential changes in temperature and volume, we can write a very general differential form for U, which is the change in U, as the partial of U with respect to temperature at constant volume times dt plus the partial of U, which is a function of temperature and volume with respect to volume, at constant T times dV. Okay, so this is a very general form for a differential of a function. And we can write this for U because U is a path independent or state function. And so we can hold one of the variables that it depends on constant while we change the other. It doesn't affect the overall change in U. And that's because it's a state function. Okay, so we looked at the case where you have an isolated system, and we looked at the case where we have an adiabatic system. And I just want to remind you that if we have adiabatic constraint or an adiabatic process, this just means that dq is going to be 0. And if we integrate over the whole process, which is just going to give us Q for that process, that will be 0. There's no heat interaction in an adiabatic process. Okay, so there's no heat interaction. I want to emphasize, though, that in an adiabatic process, delta T may not be 0. Okay, so just because there's no heat interaction doesn't mean that the temperature cannot change. You can have an adiabatic process that occurs in a system, and you may not have any heat interaction with the surroundings. So Q really, right, if you recall, this is why we made this very explicit from the beginning. If you have system and surroundings, the heat that we discuss is really this interaction between the system and the surroundings. So you can imagine, let's say you have a container, right, and it's insulated. Okay, and so this stuff is insulation. Okay. If it's insulated, and we assume it's perfectly insulated, then there will be no heat interaction with the environment. So let's say our system is enclosed in this container. Okay, and this also means that Q for any process is going to be 0 because we have insulation, and so it's adiabatic. And it's adiabatic because there's no heat interaction between the system and the surroundings due to the insulation. However, if in the system we have something that leads to an exothermic reaction going on, right? If we have an exothermic reaction, well, heat is going to be liberated through that reaction. Okay? And since there's insulation around this container, that heat can't go anywhere except stay within the system. And what that's going to do is cause an increase in the temperature of the system. Okay? So if you think about this, let's say you're going to run a reaction, right? You have this insulated container or vessel in which you're going to run the reaction. You find a way, let's say you have some ports, right? You can introduce your reactants and products independently, right? So in one port, you might have your reactants. Sorry, you don't need to reactant 1. Sorry, you're not going to put in your products yet. And here maybe you have reactant 2. Okay. They both go in, and then there's a reaction. Okay, after some time perhaps, or what have you, and that leads to an increase in the temperature of the system. And your system, of course, is going to be something that has a change in moles, because of course reactant 1 and reactant 2 will not be the same amounts as they initially are. But that's okay, because the system is defined to be whatever is in that container. Okay, and so in this case, even though the process, when you consider the system and the surroundings, is adiabatic and hence no heat interaction, the temperature of the system will increase given that we have an exothermic reaction that takes place. Okay, so I want everyone to be very wary of this difference or subtlety in terms of adiabatic processes. Adiabatic processes, because students make this, confuse this every year, and I want to try to prevent this with this class. Just because a process is adiabatic does not mean delta T or dt is 0. It does not have to be. And more often than not, delta T will not be 0, exactly for the reasons I discussed in this example here. Because heat has nowhere to go, if it's needed for a reaction or a process, or generated by a reaction or process, temperature will have to change just by the very nature of the system setup, because that heat can't go out to the surroundings, or the surroundings can't pump heat into the system. Okay, so be very, very careful if you're given a problem, and you've probably already seen this. When you say adiabatic process, don't assume automatically that delta T and dt is going to be 0. Okay. Okay, so let's go on. We can have a constant volume process. This is so we looked at adiabatic, isolated. Let's look at a constant volume. Constant volume process. Okay, and in this case, we know that dV is going to be 0 because the volume doesn't change. Okay, and so in integrated form, delta V is equal to 0. Okay, so it's a constant volume process. So we know then that dW, in its most general form, which is minus P external dV, this is going to be 0. There's going to be no work, okay, for the purposes of our class. So what that means is then du, which we've said is a function of temperature and volume, is going to be equal to dq, but now under the constraint of constant volume, we're going to write this as qv. Okay, so this is the heat interaction between system and surroundings at constant volume. Okay, so that's what that means. Okay, and we know that Q, since it's a path-dependent function, we can have heat interactions at constant volume or constant pressure. In this case, we have explicitly said that it's constant volume. So we indicate this by dq sub v. So this is actually very interesting. We can write dq sub v now. We saw this earlier as the constant volume heat capacity, C sub v, which is a function of temperature in general, times dt. So we saw this a few lectures ago. This is how we can say or write or relate heat to changes in temperature, okay? And since this process is constant volume, we have to use the constant volume heat capacity, C sub v. So we can write du, which is now a function of temperature and volume, as C sub v of T dt, where this guy is dqv. And again, this is only at constant volume. right? So we can write this at constant volume. This is actually very instructive or insightful, okay, because we can use our expression for the general differential of u and see what CV really is. And this is very simple. It's actually a very fundamental result now of thermodynamics. So we know that du of T and V, which we just wrote up here, right, is the sum of two partial derivative terms, okay? Since volume is constant in this process, we said it's a constant volume process, the second term is going to be annihilated. There, it's zero, dV is zero. So we're only left with the first term. And that first term is the partial of u with respect to temperature at constant volume times dt. And that's nice. We have this partial derivative at constant volume. That's exactly what we stipulated for the process. So let's go back. We know that we don't have to worry about the dV term. So we can write here for du, partial of u with respect to temperature at constant V times dt, okay? And when we compare these two expressions, we actually get something very insightful about what CV is, what the heat capacity at constant volume is, defined in a very fundamental way. So now this is the most fundamental way to define C sub V. The way it was introduced to you before, perhaps in Gen Chem or any other course, I have no idea where you were first introduced to this expression, but this is more or less a phenomenological relationship, meaning that it's based on our observations, right? You may have some idea of estimating the amount of heat you input into a system, okay, based on some other experiments or correlations. You measure the delta T that is associated with that introduction of heat, and then you do some regression, or you try to fit the function, and you find that it's proportional to first order to something that is CV. Okay, so this approach is phenomenological, meaning that we base it on our observations or something that is palpably measurable. When we connect it to this expression, right, we see that a very fundamental definition of this constant volume heat capacity turns out to be CV of T is equal to, now it's a definition, it's a thermodynamic definition of the partial of U with respect to temperature at constant V. So this is now one of the first things that well, we've seen many things, but this is going beyond what you've seen or been told or have been introduced to for the constant volume heat capacity before. The constant volume heat capacity is by definition, by thermodynamic definition, the partial derivative of the internal energy of a system with respect to temperature at constant volume. So it's a very, very specific thing. Okay, there's a lot of words here, very compactly represented in this expression. So the constant volume heat capacity, which is a function of temperature, okay, is defined thermodynamically as the partial derivative of U, the internal energy, with respect to temperature at constant volume. Okay, this is the rigorous thermodynamic definition. Okay, and you can apply this anywhere now. So CV of T, right, is always the partial of U with respect to temperature at constant volume, given that you can write U as a function of temperature and volume. But this is obvious. You couldn't take the partial of U with respect to T at constant volume if you were not some function of constant volume. Okay? So this is the most rigorous and most fundamental definition of the heat capacity at constant volume. Okay, any questions or comments? And so this is very important. Yeah, so let me write a few more. Thus, we can write du now of T and V is equal to CV of T dt plus partial of u with respect to v at constant t times dv. Whoops, let me, I still feel like I need to write t and v here. So does everyone see how I got to that final relationship? Because we know that the partial derivative of u with respect to t, a constant v, is cv. Hence, we can write that as cv of t dt right here, and we have this other derivative still left. Does that make sense? Is there any issue with that or discussion? Okay, good. All right, folks, give me 1 minute. I'll be right back. All right, we're back. Sorry. My laptop was out of power. All right, so any questions up to now? So we can write our total differential of u in terms of this expression. Okay, again, any comments or questions as to how I arrived at this? Okay. So as I said, CV is something that we can obtain experimentally. Okay, and we can obtain it experimentally because it's phenomenological. We have this relationship that allows us to get CV of t. Okay, experimentally, we can actually do experiments to arrive at a value for that as a function of temperature. So the next question is, what is the second partial derivative? Is there any experimental way that we can get this second partial derivative? This one. What is that? Okay, so CV is obtained experimentally, but what is the partial of u with respect to volume at constant t? Is there any way that this is something we haven't seen before, okay? We haven't seen this. And is there any way that we can get at this experimentally? Okay, and so we're going to answer that question next. And the answer, of course, is yes. Okay, and the way we do that is the Joule free expansion experiment. Okay, and this experiment is good because it's going to now allow us to apply a lot of these concepts that we've learned all the way up to this idea of using partial derivatives and applying them. Okay, so now we're going to study the Joule free expansion. Okay, so the Joule free expansion and the point that we're addressing is what is partial of u with respect to volume at constant t? That's the question we want to answer. And so through this experiment, the Joule free expansion experiment, we should be able to answer this. And so here's the experiment. I'll give you the experiment first. Okay. So we have a container. Okay, and the container is insulated. And so this is insulated. Okay. So that's good. That means that dq is equal to 0 for this process. Okay? Because we have insulation, our system is going to be within this container. Here's a container or a vessel. Okay? And inside is going to be our system. And the system is going to be in this manner. Initially, I have a partition. And that partition is going to separate two sides of this container that's insulated. Okay. Now on one side, we'll have gas. Okay. And on the other side, we'll have vacuum, meaning we'll have nothing. So by vacuum, I mean nothing. There's no gas. It's just somehow we use a pump and we reach a really, really low pressure. Essentially, we'll have a vacuum on the right-hand side. So there's nothing. Okay, so that's our setup. And in the experiment, what we're going to do is remove the partition. So the experiment involves remove the partition. Okay. And we can do this, it could be fast or slow. All we're going to do is remove the partition. It's irrelevant how fast or slow we do it. Okay, everyone get the point, the experiment. So we have initially gas at V1, let's say. Okay. And on the other side, there's nothing. Okay. And after the experiment, what we will have is our container, and you'll have to envision that it's the same size, even though it may not be drawn the same size. And now we have gas on both sides, but we have now V2, okay? And of course, it's still insulated, and that hasn't changed. Okay, everyone okay with that? All right, so we know, so far, we know that dq is equal to 0. Why? Because insulated, and so this is adiabatic. So this is an adiabatic expansion of the gas from this initial volume, V1, to a final volume, V2. Okay? All right, so now I'm going to ask you all a question. What is dW? So for this process, if you were to follow it over time, as you know, whatever time resolution you want, at any instant of time, if you were to have very small chunks of time, you could think about dW, this differential amount of work. So what is dW in terms of, so how would we write this in the most general form? Let me help you with that. dW is just,
It would have to be du, because it's adiabatic, so there's no dq.
okay. There is no, okay. So you're right. So du is going to equal dw. This is the application of first law. That's right. And so what is dw? So does everyone follow how I wrote this? This is the application of the first law. Du is equal to dq plus dw, but dq is 0 because it's adiabatic, so we're left with dw. And we have a very general expression for dw, right? And that general expression, because I haven't mentioned at all in my discussion whether this is reversible or irreversible. I think all of you may have an idea as to what this is, but I'm not going to say it yet at the moment. But this is the general expression for du in terms of dw, which we know is minus p external dv. Does everyone follow that? Okay. What can you say about this minus p external dv term with very precise certainty? So here's the gas, okay, right here in our initial box. And on the other side of this partition, when we remove it, is vacuum. And so what's going to happen when we remove this partition is that the gas is going to expand to the right, where we have vacuum initially. And so we're asking about the work that the gas does as it expands from that initial volume V1 to fill up V2, which is the entire container.
It's going to be negative.
Why?
Because it's going to be a positive difference in volume.
Okay. Okay, so there's two terms in there's two things being multiplied in that work expression, dW. In this case, we're going to have to look at both of those terms. Yeah, go ahead. I cut someone off.
I was going to say P external changes because the vacuum is going to have, essentially no pressure compared to the original container.
Okay. So what does that imply?
That it's irreversible.
Indeed, this is irreversible. This is an irreversible process. Yeah, we'll revisit this again when we look at entropy, because we know that for irreversible processes, entropy increases. But anyway, I'm jumping ahead. This is indeed irreversible. But what else can you say about P external? So dV, yes, is positive. That is true in this case. But we still have to look at the P external term. So let me think about it this way. Let me pose it this way. The instant we remove that partition, right? What is external pressure on the gas, which is our system? So our system is the gas. I think everyone pretty much gets that much. Not the vacuum, the gas. The gas is our system. So the instant I remove that partition, what is the external pressure that the system is exposed to?
The container? Would it be the container?
Okay, so what numerical value? What would be the numerical value the moment I remove the partition? So let me put it to you this way. If be a molecule, if you're one of these gas molecules, okay, when that partition is there, okay, you're going to be exerting this pressure. It's my pressure. It's the internal pressure, the equilibrium pressure of the gas, me and my buddies, right? We're hitting the walls. There's some internal pressure. Now, all of a sudden, somebody removes this partition, right? So, and I see, oh, well, there's now more volume in front of me. If I'm one of these molecules at the edge or very close to that partition. But what is the pressure that I would see ahead of me? If
Zero.
Yeah, exactly, zero. Why?
So the work would be zero.
Why? Okay, good. Why did you say, okay, very good. Why did you say zero?
It's a vacuum, so there's nothing over there, so there's no pressure. As soon as you open it, like you said, the instant you open it, it's be zero.
Exactly. And so now, all of us, me and my buddies, move up, right? But as we're moving up as like a bunch of soldiers marching, what do we see ahead of us? Because we're the system. We're the system. So, of course, our boundary is going to move. But outside of us, because we're the system, is the external. But what is the pressure that we see? It's always going to be
zero.
Zero, because we're moving into a vacuum. Okay, and so in this case, that external pressure for the whole process, the external pressure, not on the gas is the system, right? So the external pressure is what is outside of the system is always going to be zero. And in that case, then none of us does any work as we expand. It's a very interesting process. It's a very interesting experiment, but there's no work done. And it's because there's a vacuum external to the system. Okay. So even though the volume increases, there is no work. So because, sorry, I don't want to put it there yet. Because gas expands into vacuum, P external equals 0 for entire process. Okay, therefore, VW and the integrated form of work will be 0, and W is 0. Okay, is everyone clear on that? So this Joule-free expansion, we'll see again. That's why I want everyone to, if you don't get it now, think about it. It's very simple. It's not that complex. The gas is our system and it's moving into a vacuum and it doesn't see anything there. So there's nothing, there are no molecules outside to present a pressure to the gas as it moves and so the gas isn't working on anything. So there is no work. Or exerting force on anything, so there's no work. So in this case then, du, which is equal to dq plus dw, but we know dq and dw are both 0. This is a case where the energy, the internal energy of our system remains the same. There is no change. So even though we have this expansion, the internal energy of the system doesn't change. And so what kind of a system is this? It's an isolated system. Okay, and we could have said that this would be the result even before because we knew it was insulated and there was no way mass can go in and out. So it's an isolated system. And we saw that for an isolated system, if we have that constraint, du is going to be 0 and delta u will be 0. So u is a constant in this case. So this is very useful. We can use this now, okay, because it's an isolated system. We can use this result or this experiment. And let's go back. So recall du, which is equal to now CV of t dt, plus the partial of u with respect to volume at constant t times dv. Okay. And this all is going to equal 0 in this case, right, for the Joule-free expansion experiment. For this experiment, this is going to equal 0 in this case. So we can use that information to rearrange and solve for this guy, because that's what we were interested in. That was the whole point of our discussion, which was, what is this partial derivative? Okay, but we have a way to get at it now. So this is how we can do this. Okay, so this guy is all going to equal 0. So let's just rearrange and isolate a few things. So I'm going to say that minus CV of t dt is equal to the partial of u with respect to volume, the constant t times dv. Okay, so all I did was bring the CV term to the left by subtracting it from both sides. Okay. Any questions on that? Okay, let me make sure that, okay, and then we can isolate this term further by saying that minus CV of t dt dv, I'm going to bring the dv over, is equal to partial of u dv at constant t. Okay. Now I'm going to qualify something here because u is constant. in this experiment. And so U is constant by design. The experiment is done in such a way that U is constant. Okay? We actually control this fact. We actually control this behavior. The experiment is set up so that U is constant. So we have minus CV of t. Here we can write the partial of t with respect to v, but here we're going to qualify this by saying this is a constant U. Why? Well, because we did the experiment at constant U. We set up the experiment. Okay, we did it. So we can do that. It's okay. We're allowed to do it. You can do this in your PChem lab if we actually had the capability to do this in person, this experiment. So we now have a relationship for this partial derivative that is given by this. Okay, and that's actually pretty cool. So we weren't sure what this partial of U with respect to volume at constant t was, okay, but we sort of kind of engineered an experiment. Joule did. He kind of came up with an experiment that would allow us to have access to this partial derivative, potentially in terms of things that you can measure. Okay. Now let me just say this. U is something that you can't directly measure. There is no dial for U. Okay. There's no meter. Let's say like a pH meter or a thermometer or a pressure gauge, right? Those are instruments that you can use to measure those properties, but there is no instrument that you dip into some solution or some material and it gives you U equals a number. You can't do that. Okay, you have to do it indirectly, and that goes for its partial derivatives as well. And for instance, the partial of U with respect to any other property. So this relationship, by designing the experiment as we've done, allows us to connect U, the partial of U, with respect to volume, to things that we can measure. Okay, so we can measure CV. We can measure CV as a function of temperature independently. And then we can also measure temperature and volume under the conditions of this experiment. Okay. And so the way one would get partial of U with respect to volume at constant T is the following. In our experiment, what we would do is we would change the different delta V's, right? So we see here that the gas is expanding from initial volume V1 to final volume V2. We can change the V1 or the V2, or essentially delta V. We can have this gas expand into different final volumes so that the delta V is different in each experiment. We can do 100 different experiments, each with a different delta V. Okay, that's easy to do, right? You just have different volumes, different size containers. So you can always control the delta V. You can always control the delta V. So this is going to be minus CV of t. We can write this dt dv as delta t over delta v at constant U as an approximation. But then what we're going to do is take the limit as delta v goes to 0. Okay? So remember how derivatives were these limits where things go to 0, where they become very, very small? So in this experiment, what we're going to do is have a whole bunch of experiments where that delta V is something that we control and change from experiment to experiment. And we're going to start at large values of delta V, and then we're going to make delta V smaller and smaller and smaller and smaller and smaller. Okay? And when we do that, we're going to measure the delta T that happens after the gas expands. So we can measure the T initially, and we're going to measure the T final. Okay? We can measure that. That's fine. We can measure it with the thermometer. That's not something that's outside the realm of measurement. So here we have two things that we can measure, delta T and delta V. Delta V we set up by construction. CV of T is something that we can measure experimentally in a separate experiment. Okay, using the dq is equal to CV dt relationship. And then when we take the limit of this product as delta V goes to 0, based on our experimental setup, we can extrapolate to delta V equal to 0, and we see that we get this partial derivative that we had no idea of how to get beforehand. So here what we've done is replace or connect, not replace, connect this rather abstract, esoteric partial derivative, partial of U with respect to volume at temperature, to something that is experimentally accessible and experimentally measurable. Okay, so du dv at constant t then becomes this limiting value of the product of CV over T times delta T over delta V at constant U. And that constant U is the joule-free expansion experiment. Okay. Any questions? Any questions at all? One final thing I want to say here, that partial of U with respect to V at constant T is equal to 0 for ideal gases. And only for ideal gases. And so this is another important result. So this is one important result, and the other one is that. So partial of U with respect to V at constant T is equal to 0 for ideal gases. Okay? So for ideal gases, du is equal to CV ddt only. And so U is a function of T only for ideal gas. Okay. Any questions on that? So for real gases, this is non-zero. Okay. It's only for ideal gas that this partial derivative is equal to 0. And in fact, we will use thermodynamics and rigorous equations later to show that. We don't have, right now I'm just telling you, but later on, when we get a little bit more sophisticated with some of our ideas, we will be able to actually show that this is true. We will be able to relate U to an equation of state, and then we'll show this, and you will see that it equals 0 later on. It's very cool for ideal gases. Okay, as usual, I've talked too much. Any questions, comments? Okay. Well, I will post the lecture, and again, Thursday, October 8th, 7 to 9 p.m. Looks like our first midterm, and I hope everyone will be excited for it. Have a great weekend. Be safe, and I hope you can enjoy the great fall weather. And so I think I will end the meeting at this point. If there are no questions.
Thank you.
Thank you.
Have a great weekend.
Yep, you too. Thanks all.